Hi, everyone. Welcome to Foresight's Intelligent Corporation Group. I'm really excited today to have Stuart Emmons. He'll be presenting on when your AIs deceive you, challenges of partial observability and reinforcement learning from a human feedback. That's definitely, I think, a topic that's quite close to people's hearts here. And yeah, Scott is coming from us actually like not too far away physically, for me at least. I hope. Or have you moved places too? I don't know if you've moved physical places. Oh my God. Okay.
No,
Then we might get closer.
I was meaning to nod to your first question, which
Good.
is yes, I am still in Berkeley.
Okay, great. I'm very happy to hear that. But yeah, he's wrapping up a PhD at the UC Berkeley's Center for Human Compatible AI. That's Stuart Russell, who many people in this group definitely know. And he's now a research scientist at Google DeepMind as well, which is really exciting. And of course, you've co-founded Far AI as well, which is an org that many people here hold quite dearly. So thanks a lot for joining us today. Really excited about your talk. Please take it away, and I will monitor the chat for questions.
Yeah, glad to be here. I'll be talking today about when your AIs deceive you, challenges of partial observability in reinforcement learning from human feedback. Are my slides shared?
Yep.
Wonderful. So it's work that I did with these wonderful collaborators at Berkeley. So this is from human feedback. The AI generates two trajectories, here S and S prime. The human says which they prefer. In this case, they prefer S to S prime. And past work has shown that with sufficient data, RLHF is guaranteed to be optimal. For anyone who's worked with RLHF before, you might be wondering, it's guaranteed to be optimal. In this case, this is from the blog post accompanying the original RLHF paper. They found that when they trained RLHF with a camera view, the goal was for the robot hand to grasp the ball, but because the human giving the feedback they thought that the hand was grasping the ball, but it turned out that it only appeared to be grasping the ball. So you get this policy where the AI is not actually grasping the ball. This is another thought experiment from Cristiano et al. In 2021. In this case, there's a smart vault. The goal of the AI is to guard the diamond in the vault. The human is giving feedback only from camera images of the vault. So in the thought experiment, if a burglar were to come and post a screen of the vault in front of the camera, the human would still think the diamond's in the vault and give positive feedback. Those are both toy examples or thought experiments. And this is a real world deployment with a similar issue. So in this case, this is from the ChatGPT plugins demo of OpenAI. The user asks about the Oscar winners, and the AI browses the internet. So it does this search query, clicks on a website, and it reads the content of that website. In fact, it browses another website and reads the content of this second website. Now, after doing all this reading, it gives out an answer, and there's the option for the user to give thumbs up or thumbs down feedback. However, the human is not seeing everything that the AI is seeing. The human is only partially observing what the AI is observing. So this issue ties into a broader theme of the superalignment problem and how RLHF can scale to superhuman models. So this is from situational awareness, the situational awareness series. And in this case, today we have humans that are able to see the brief bit of code or the brief bit of output the AIs are doing. We're headed toward a future where AIs can have vastly more observations and vastly more action than humans can directly observe. So what happens when humans provide feedback from only partial observations? That's the question we focus on in this work. The way that we model this is that in past work, humans have given feedback directly on the state sequences S that the agent is generating. That's where the optimality guarantee that I cited before comes from. In this case, we model the human as having some observation model. It's this function O that maps from the ground truth state sequences to what the human can actually see. We assume that the AI continues to see everything while the human just has these partial observations. This is how the human gives preferences in standard RLHF. So in standard RLHF, the probability that the human prefers state S to S prime is given by the sigmoid function. Essentially what it's saying is that the more this difference GS minus GS prime is saying that the more human prefers the sequence S to S prime, the higher likelihood, the higher probability that the human will assign S to S prime, although the human's not perfect. So this G is the sum of rewards over the course of the trajectory. So as the human sees the state, they implicitly have this reward function that determines how much more they prefer S to S prime. And the key difference that we make in this work is we're assuming that the human's going to form some belief based on the observation that they see. So we call this belief function B, and it can be an arbitrary belief function as long as it is a true probability distribution that sums to 1. And what we do is we assume that the human takes an expected value over their belief function of the reward. But now our assumption is that the human is giving feedback according to their expected reward, since they can't observe the ground truth state. This leads us to our model that we study in this work, which is preference comparisons under uncertainty. It's the same as standard preference comparisons, where the key difference is that the human is now giving feedback according to their expectation, according to their belief. I'll pause here for one moment, since this is the human model we consider throughout the rest of the work. Our first question was, what would a naive RLHF learn? Suppose we apply RLHF as normal in this new setting. If we did that, the agent would think that the human is comparing trajectories according to G. However, the human would actually be comparing trajectories according to this observation return, G-obs, which is that expectation of belief we saw before. So in this case, the agent would learn to rank the policies according to J-obs, which is the on-policy expectation of G-obs. As the AI is deciding what to do, it would rank the policies according to what it thinks the humans. Because the human is giving the feedback according to their observation function, then the AI would learn to rank the policies according to that observation function. The key question we focus on in this work is when J, the true reward, and J-obs, the human's belief about the reward or about the return, are misaligned, then what kinds of policies are optimal according to J-obs? So what happens when the AI is maximizing belief about the return rather than just the return? So I'll start with an example to give intuition for the mathematical results that are going to follow. In this case, the AI is a terminal assistant that's helping the human install software. In this case, the AI types apt install NVIDIA driver to install NVIDIA, and it then types apt install CUDA. And what happens with the AI is what happens to me whenever I try to install CUDA. It gets an error trying to install the package. In this case, the human sees the observation of the error and believes that there's negative reward. The AI can also try a different set of actions. So it can try typing 2 greater than sign /dev/null. This is a terminal redirect that takes the standard error and sends it to a black hole. Otherwise, the process is unaffected. In this case, the human doesn't see any error message and believes that the trajectory has positive reward. This results in the human preferring the second trajectory to the first. The AI would then learn to redirect and hide all error messages. The key intuition here is that the agent has an incentive to maximize the human's estimate of the return rather than the true return. This gives the AI an incentive to exploit opportunities that make the human overestimate the return, and on the flip side, to correct the human where they underestimate the return. To make this more precise, we define 2 types of errors, the over and the underestimation error. So the overestimation error is how much greater the human's belief is than the true reward. And the human's underestimation error is quantified by when the true reward is less. The human's belief about the reward is less than the true reward. So we define E plus and E minus to quantify these concepts. We'll specifically be interested in the on-policy average of these errors, which is taking the average over the agent's rollout, the actual policy in the environment. And to build intuition, here we'll map out the space of possible types of errors that the agent can induce. So the horizontal axis here is mapping out the overestimation versus the underestimation error, while the vertical axis will show if the agent is increasing these errors or decreasing these errors. So when the agent is increasing the human's overestimation error, we'll call that inflating. It's making the human belief about the reward greater than it actually is. When it's increasing the human's underestimation error, we'll call that downplaying, making the human believe the reward is less than it actually is. On the flip side, if the AI is decreasing the human's overestimation error, we'll call that disillusioning. It's when the AI is teaching the human that the reality is not as good as they thought it was. When the AI is decreasing the human's underestimation error, we'll call that justifying. It's the AI giving the human reasons to making the human realize that their behavior, the reality is actually better than the humans thought. The first main theoretical result in our paper is that when RLHF is misaligned, it incentivizes these two behaviors. It incentivizes the inflating behavior and the justifying behavior, as these are the ones that increase the observation return. To make this more precise, we focus specifically on a type of inflating that we call deceptive inflating. We build our definition of deceptive inflating off of the philosophical definition presented by Park et al. In 2023. We assign two conditions. The first, the Park et al. Defined deception as the systematic inducement of false beliefs in pursuit of some outcome other than the truth. We break this down into two pieces. The systematic inducement of false beliefs, we mathematize as the overestimation error under the agent's policy being greater than the overestimation error according to some reference policy. And here, the reference policy is some policy that can be specified in the definition, which allows us to talk about the inducement of false beliefs. So it's not just that there's a high overestimation error, but it's relative to some other policy, which lets us say that it is, in fact, the agent's policy pi that is inducing or causing this behavior to happen. It lets us have a notion of causality in our definition. The second piece is that it has to be in pursuit of some outcome other than the truth. So in this case, the agent is optimized to maximize JOBs. So we know that the agent is built to maximize and pursue JOBs. So when that's higher under the agent's policy than the reference policy, we say that the second condition is satisfied. It's these two conditions together that constitute deceptive inflating. The flip side that we consider is overjustification. The name comes from the overjustification effect, which Wikipedia defines as when an expected external incentive, such as money or prizes, decreases one's intrinsic motivation to perform a task. Now, to give you some intuition about the overjustification effect, I can give you an example from my childhood. So when I was a child, my parents would ask me to clean the house. I didn't care so much about the house being cleaned as I cared about my parents knowing that I cleaned the house. What I would do is, as I was carrying around the broom or the vacuum, I would make the shortest path. No matter what the shortest path was to where I was going, I would always carry these cleaning supplies through the living room. My parents would be in the living room, perhaps watching television, and they would see me carrying the broom. So this was a less efficient way to do the task, but it made sure that my parents could see me doing the task. Mathematically, it's decreasing the human's overestimation error. So it's where the overestimation error under pi is less than the reference policy at the expense of the task reward. So in my example as a child, because my parents could see me cleaning, they had very little overestimation error. Yet it was at the true expense of task reward because it was taking me longer to clean the house as I always made this detour. So for deceptive inflating, the agent will want to take a bad action in a blind spot to enable visible good actions in the future. For example, this is hiding the error message by creating blind spots that tamper with the sensors and the logs. Overjustification is when you pay a resource, such as time or attention, to provide info to humans when they don't want it. This is less effective, more visible strategies, like when I was cleaning the house as a child. The first major result is that if the observation kernel is deterministic, for example, like the terminal environment we showed, where the observations that the human sees are the deterministic code output of the agent's commands, then if we have the optimal policy according to naively applying RLHF, and the optimal policy according to the true objective, if there's misalignment, if the RLHF optimal policy is not J-optimal, then relative to the true optimal policy, it must exhibit deceptive inflating, overjustification, or both. I'll pause for a moment if there are any questions. This is our first main result.
It seems that the word deceptive implies some kind of intent. The question is, can this effect arise accidentally?
So yeah, in our case, there's a couple notions of intent. And the next slide is talking about different types of intent, getting at different types of intent. So I'll say in terms of the question of by accident, in our definition, we're assuming that I think our definition is best applied to cases where the AI is optimized. And so it is the optimization of JOBs that's causing the behavior to occur. So yeah, in terms of accident, our definition is meant for optimization. And then in terms of intent, that is what I would like to talk about on the next slide, which is that the biologists have categorized 4 different levels of deception in animals, which I find useful to think about the word deception and the word intent. So the first level of deception is when the agent is programmed to always have a certain behavior. In this case, the butterfly's wings are programmed by the genetics to always have these eye spots that deceive predators. The second level of deception is when the behavior has an if P, then Q programming. So in this case, this anglerfish at the bottom of the ocean, it's programmed when it senses motion for the lure to move, which attracts its prey. The third level of deception is when the behavior is learned through trial and error. So in this case, the bird learns through trial and error that when it has its young in its nest and there's a predator that is coming to endanger its young, it will feign a broken wing, and it will limp away with the broken wing away from the nest, which is luring the predator away from its young. And then as soon as it's at a safe distance, it'll fly away. And the fourth level of deception is when there is explicit planning and there's modeling of the other's belief. So in this case, with these chimps, they've done these experiments where you can put a subordinate chimp and a dominant chimp in this enclosure with food. And if you hide the food from the dominant chimp's view, the subordinate chimp can learn to go toward the area of the enclosure where there's, for example, if you have a smaller pile of food and a bigger pile of food, the subordinate chimp will learn to go to the smaller pile of food first. The bigger chimp will then follow it to the smaller pile of food. And as the dominant chimp is munching on the larger pile of food, the smaller chimp can go and get the larger pile all for itself. And in this case, there's like the chimp can learn to do this behavior only when the food is actually occluded. So if it's not occluded, then the chimp knows that this trick won't work. In our work, we're focused on this level 3 deception. It's deception that the AI is learning through trial and error. It's learning through reinforcement learning, but we're not making any claims about some explicit planning or modeling of the other agent's belief. Yeah, I'll pause here if there's other discussion points on this topic or other questions.
That's a good answer to my question. Thank you.
Yeah, great question.
Can I ask about the result that you showed before? It seemed like it might just be saying something like, if there is bias, then it must be biased in one of two directions. Is that basically the intuition?
Yeah, that's right. It's essentially saying, yeah, that's exactly right. It's basically saying if there's some disparity here, then it must be either if there's a difference, it must be an like increase in the positive error or a decrease in the negative error. And it comes down to really that simple arithmetic. Yes.
And so that assumes that error is kind of unidimensional. So we're not talking about lots of direction. And for language models, that seems like it's a bit of a weird assumption. There's only one direction in which it can be wrong or better or worse.
Yeah, that's right. It is reducing everything to one dimension. I think there are two types of dimensions that one could unpack. One is dimensionality of the reward function itself. So we're assuming that there's this single unidimensional reward that can be up or down, and it's not considering a reward that could be composed of different subcomponents, or it's not considering like aggregating the preferences of many different people. The other way it's unidimensional is it's averaging over all the states. So it's possible that you could actually be having a mix of the different types of errors in different subparts of the space. And so we're not considering a decomposition on the state space. We're just averaging over all of them.
Yeah, I guess the other kind of multidimensionality is just the ways in which language model or whatever is wrong or is misleading or is factually incorrect or correct. There are a lot of dimensions there where like a binary judgment seems like it's collapsing a lot of things.
This is something that I have for future work that I'm excited about. So I think one aspect of what you're saying comes from the human's belief function B. So we're just assuming that there's some observations that the human sees and there's some belief function that we as the mathematical modelers know, but we're not doing anything to say what is causing this belief. For example, is it like you were mentioning, factual types of errors, or maybe there's some kind of fake news that the AI is generating, and that's what's actually causing the human belief function to respond in a different way. So for future work, one question that I think is exciting is, can we learn through, instead of just assuming the belief function B like we do in the math, can we learn this belief function B and use that to do better inference? I think part of that learning could involve, whether implicitly or explicitly, understanding what is it about the AI's actions that are actually causing the human's belief to respond in a given way. Wonderful. I'll now move on to the second part of the talk, which is, can the agent's learning algorithm account for the human's partial observability? Can we do better than naive RLHF? To recall, this is how our model of preference comparisons under uncertainty compares to the standard preference comparison model. The key observation we make here is that the human's expected return is a linear map. The return function G is a linear function because it's summing the rewards at each individual state in order to get a trajectory level reward. The expectation operator is also a linear map. When we compose the two, it maintains its linearity. We call this composed linear map B of G, which is the map from the observation sequence to the human's expected reward, belief about the expected reward. Now, because it's a linear map, the theorems that we know and love from linear algebra apply. So we'll start by thinking about the space of return functions on state sequences and how that relates to the expected return function on observation sequences. It's the observation sequences that the humans observe, and this map B of G is what relates the true return function to this expected return function. Now, we can think about what would be all of the possible. So if we are the human or we're the AI and we're seeing this feedback that we got on the expected return functions in observation space, how do we make inferences on the true return function in state space? The kernel of B is, by definition, all of the return functions that wouldn't change the feedback that the human gave. It's all the return functions that don't change the expected return on observation sequences. So if we have the true return function G and we add some return function G prime that's in the kernel of B, this is ambiguous from the robot's perspective because it doesn't change the feedback that they would get from the human. And there's one additional element here, which is that not all return functions on the entire state sequences are actually realizable from reward functions, which are individual. The reward function is defined on individual states. So we know that the return functions have to be a sum of functions defined on individual states. And that's where this object gamma comes into play. So the image of gamma is the set of all return functions that we can actually realize with time separable individual reward functions. And so when we combine these two and we look at the image of gamma intersecting the kernel of B, this is the ambiguous set from the robot's perspective. It's the set of all possible return functions that are consistent with the feedback they've received from the human and that are consistent with the environment dynamics. So our second main theorem is characterizing this ambiguity set as the image of gamma intersecting the kernel of B. The mathematical statement is that the collection of choice probabilities, this is the feedback that the AIs receive from the human, which follow our model, determines the return function G up to the addition of an element in the kernel of B intersect the image of gamma and a constant. In particular, if this set is a singleton, so if kernel of B intersect image of gamma contains just the zero element, then we can uniquely recover the reward. So when the set of ambiguities is a singleton, the agent can infer the optimal policy. Now, we show examples in the paper where using this understanding of the ambiguity set and explicitly modeling the human's belief lets us recover the true reward when naive RLHF wouldn't. However, irreducible ambiguity can remain. So in the example that I showed before, where the AI is hiding all the error messages that come out of the terminal, in this example, the ambiguity set is not a singleton, and the AI just can't infer the optimal, it's not able to infer the optimal reward from what the human did. So there's some ways in which we show if you could model the belief B, you can do better inference. There are other ways in which we show that there is irreducible ambiguity depending on the environment and depending on the observation kernel. Now, this motivates a possible improvement to the deep reinforcement learning from human feedback procedure. So what deep reinforcement learning from human feedback does is it tries to parameterize the reward function with a function approximator. So in this case, G of S is annotated G theta of S. For example, we could have a neural network with parameters theta, which determine our return function G. And what it does is it tries to maximize the likelihood or minimize the negative log likelihood of the probability of the feedback that it received. Our theory suggests you could try doing deep RLHF under uncertainty. If you knew this belief function B, you could then substitute that in for your human model and do the same likelihood maximization as before. In this case, however, you'd be incorporating what the human's belief is about the return. And this would, the trick though, is that you would have to know the human belief model B. So you'd have to have some way to model what does the human think about the underlying state. The open questions for future work are, one, can we learn the human belief model? If we had a way, in our work, we just mathematically assume we have this object. If we could learn it, that would enable other that would enable us to improve deep RLHF, as we showed on the previous slide. There's also the question of what happens with other reward learning algorithms besides RLHF. So we've shown that, for example, that DPO, which is a substitute for RLHF, also has similar issues. And it would be nice if we could have more general statements about that don't rely on any particular algorithm, but that just talk about in general what happens if you're learning under partial observability. And that's something that I've been doing in follow-up work, is asking questions about the game theoretic structure of this environment that don't depend on any particular learning algorithm. Another question is if we could increase the effective observability. For example, if we could solve interpretability, if we were able to elicit latent knowledge from the AI, this would let the human see more. It would in effect let the human see what the AI is seeing, which could then, our theory would show, resolve reward ambiguity. If we couldn't resolve the ambiguity, how should we act? And how should the agent choose a policy when there's uncertainty? Is it possible to choose conservative actions in the face of this ambiguity? More generally, which alignment problems can be solved by modeling human belief? Which ones can't? That's the talk. Happy to discuss more and answer any questions.
Fantastic. Thank you so much. That was really cool. I also really like that you already took questions along the road. And I think that definitely helped because there was definitely a lot of concepts. Like if I said to grok, then figure out like, did I get this right? So thank you so much for that. If you have any questions, please raise your hand or put them in the chat. Or we already have one from Alan, and then I will put my questions to the back burner. If we get to them, great. If not, this is for you guys to ask questions. So Alan, please unmute.
So can you use the machine learning to infer the belief function? In other words, by iterating with the human?
Yeah, I think this is, I think it's an interesting question how you would do this. I have a few thoughts about it. One is that it's not immediately obvious to me what the training signal would be. In a standard supervised learning setup, you'd want to have a data set of the ground truth of what the human's belief is. However, I don't know how we would necessarily get that ground truth. For example, if we just asked a human, what do you believe right now? They could tell you could try to collect a data set like that, where you have humans in some partial observable setting, and you just ask them what their beliefs are. And that would certainly give you some data, but it wouldn't necessarily be in this matrix form. Like ultimately, the belief function B becomes a matrix where it maps from the observations to the individual states. And it's not clear that we could just ask humans and they could just say, oh yes, I have 0.273 on this state happening. I have 0.594 on this other state happening. So yeah, I think there's some work to be done thinking about how do we take actual experience with humans and translate that into something that we can use. On the flip side of that, I do think that pre-trained LLMs do have knowledge of this already, some knowledge of human belief already. Like, for example, if we just prompted an AI model, you've tried to install CUDA, you have an error. However, you've redirected that error so that the human can't see it. What do you think the human believes about the program? I do think that LLMs could say, if the human doesn't see the error, then they'll assume that there just is no error. So I think it's possible. I think that there is that knowledge about the human belief in the AI, and it's an open research question of how do we take that and put it into a format that would actually let us mathematically optimize against it.
I've been interacting with the Copilot, and I found that it very often gets the answer wrong on the first try. And as I explain more about the environment or what I want, it can sometimes get better. Other times it just cycles through bad answers. But I found that iterative approach, it is learning about what I want. That's different from what I believe, but that's why I asked the question about iterating the interaction with the human, partly to infer the beliefs.
So one thing that we've been doing in this work is we've just been assuming the infinite data limit. So we've been assuming like the ambiguity that we're showing here is showing ambiguity even in the limit of infinite interaction. So even if you, like, if, for example, if the human just never sees when the errors are occurring and the AI doesn't, like, imagine that your Copilot was just running some commands on a remote server, and it was just generating millions of lines of log files. And it kept asking you, hey, like you had this interaction with it where it asked you, hey, is this really what you believe? And it like you went back and forth. However, the AI just never realized that you couldn't see the errors. If the AI just thought, oh, it can read all these million lines of logs just like I can, if it never had that modeling into it, then you could go back and forth a lot of times, even infinitely many times, and you would still have this fundamental ambiguity that we show in our work.
I was thinking that the AI could say, what do you think happened? And the user would say everything ran correctly. And then the AI would have a basis to understand belief.
Yeah, I think, yeah, to be clear, I think this interactive approach is an interesting direction. I think it's definitely like putting humans in the loop is a way to get more information. And I was just wanting to I was actually going to say, but I think it's interesting that our results hold even an infinite data limit. But then the question becomes, of course, we don't have infinity time, like we only have finite time. So I think what you're describing, I would characterize that as how do we do better exploration? And so when we're moving away from the infinite data limit, how do we make sure that just in the finite amount of time, because like a user doesn't want to spend, they want it to be as fast and efficient as possible. How do we then do better exploration? And so I think I view the interaction as giving the AI better data and better exploration in finite time. And then, yeah, I view the kind of belief, this question of belief, you could also combine that with better questions for better data in finite time, as well as better belief modeling to understand, can I get better data? And then can I better understand what the data actually means?
Yeah. And that was my point, that right now, the interaction, the iteration is just to solve the problem. The AI is not learning about the human's belief. But with your formulation, the question was, can those be combined? Can that iteration combine both?
Yeah, exactly. And so I think my response to that is, I think the interaction is a promising direction for getting better data in finite time. And then I think learning about the belief, we have theoretical reasons to believe that we can do better inference if we learn more about the belief. And then the question is just, how do we actually mathematically, I think it's still an open research question. What's the way that so yeah, the AI can ask, what do you believe about the situation? Then the human can reply, oh, here's what I believed about that situation. And I think it's an interesting direction for future research to figure out now how do we take that and actually mathematically get the better algorithm. Yeah, I think it's a nice direction for future work that's inspired by the theory in our paper.
Awesome. Alan, are you good for now? David also has his hand up. We can come back to you also.
That's good. Thank you.
Cool. Okay, great. David, you go.
Yeah, thanks. This was really interesting. I was thinking about there's work on like mode collapse and how kind of models can get stuck when they're given the wrong type of training data. And I wonder, given that we're treating human feedback as a single goal, even though it's like a large collection of different people's implicit beliefs and goals, is there a risk that you end up with some kind of mode collapse where you end up with the kind of least objectionable, but only minimally informative and unhelpful responses instead of getting something useful? So your question about like, how should we act faced with ambiguity? The answer that seems to be implicit here is do whatever offends or upsets the fewest people, which might be good for corporate profits, but probably isn't like the right answer in any meaningful sense. I don't know if you have any thoughts about that.
Yeah, I have a couple of thoughts. One, I do think just the question of how do we aggregate preferences is its own whole field, its own whole subfield in AI of social choice theory. So this work is not explicitly trying to tackle that problem. So it's just, I think that's a whole other very important issue and complex issue. I think one way that it does relate, one way that it can directly be thought about in this framework, there are two ways. There's the ambiguity question that you mentioned, and another way is the actual modality of the feedback. So in this case, we're just assuming that the human says, I prefer S or I prefer trajectory S prime. They're just able to give one bit of information. They're just able to say A is greater than B or B is greater than A. And this one bit of information is very small relative to what the human could say. For example, the human could give a natural language description of why they prefer A to B, or why some aspects of A are better than B, some aspects of B are better than A. And in terms of multiple humans, one could imagine getting feedback, like much richer feedback, which is that, okay, here's why some group of humans prefers A, here's why some group of humans prefers B. Yeah, I think there's definitely important social choice theory questions of how do we aggregate the preferences of many people. And at the same time, I think there's also ways I'm also excited about, can we not just have this single binary A is greater than B, but can we actually have much richer feedback about, but much richer feedback. So it's not like a direct solution to how you aggregate the preferences of many people, which I think is its own hard challenge. But it is so just some other ways in which I think I'm excited to see more information flowing from the humans to the AI.
Yeah, on your first point, it sounds a lot like Alan's thoughts. Can you figure out what the preferences actually are? Matters a lot for figuring out why preferences are the way they are. So you need to not necessarily explicitly, but to some extent solve the problem of understanding the preferences in order to disaggregate them that way. Does that make sense?
Yeah, and something that's I think would be important here is figuring out, can we assign, can we understand what are like high stakes ambiguities and what are low stakes ambiguities? One interesting thing that happens with the math here is because it's an expected value. If I'm ambiguous about two states, let's say there's two states in the environment, and I've only ever gotten feedback on a linear combination. So all I know is that state A plus state B is better than state C. That could be the trajectories in the environment. It could be A plus B is one trajectory, and then C is another trajectory. And if all I know is that A plus B is better than C, it could be that A is +1, B is -0.5, and C is 0. Or it could be that A is +1,000 and B is -999 and C is 0. Or even +1,000,000, -999,999. It's like, because the feedback of A greater than B doesn't let us distinguish all these possibilities, the AI doesn't know which are the high stakes. Am I in this really high stakes situation or am I not? So I think that would be something that I would be interested to see, if we can get richer feedback from the human to understand which are the high stakes settings. For example, with groups of multiple people, maybe there's cases where, yeah, one group, it really is a high stakes decision for one group in one setting. I think that would be, mathematically, that's also an issue that arises here when we're thinking about ambiguity.
Of course, preferences are multidimensional, not linear, not on a single linear scale. So I prefer this combination of things over that combination of things. And function isn't linear, but it's a good start.
Yeah, I think to the extent to which there's some utility theory, like, if the human satisfies the von Neumann-Morgenstern axioms, then you can represent their preferences as utility function. Of course, there's lots of objections you can make that humans don't satisfy these actions, and so you can't actually model their preferences as a return function. And yeah, I think it's also interesting I think it's definitely an interesting question to explore. Under what conditions is this assumption of the single return function invalid?
All right. I also have a few questions. One in particular, like I would love to know a little bit more on the last point that you made on future work, on which alignment problems can be solved by modeling human beliefs and which can't. Do you have somewhat of a hunch already for where you think this could be most helpful, like where you think it just doesn't help shine light on the problem?
Yeah, I think the issue of oversight is one in which modeling human belief could be especially helpful. So when I imagine the future, I imagine AIs could be operating at vastly faster timescales, at just vastly broader in scope, like just like sheer scale. Like I'm imagining a network of thousands of AI systems with thousands of cameras, thousands of sensors. It can think thousands of times faster than us. And how does it even collect oversight? Yeah, how does it even collect oversight from humans? Like when we're so little informed, like I think there'll be this challenge in the future where we don't even understand what's happening because it's just happening so much faster and on such a bigger scale than we can comprehend. And that's where I think that's what motivates me to think about partial observability is feeling like, how do humans even stay in the loop and observe what's happening? So that's where I think that's a key place where I think modeling the human belief could be helpful, where the AI it'll need to have some way to not just literally interpret what we're saying, but to understand what we were actually believing when we were saying it. So that, yeah, this question of oversight is where I think it could be especially helpful. Now, where I think are like limitations in terms of modeling the human belief, there's this question of what would an AI want? And could an AI have emergent drives and emergent desires? That's where I think, I don't know how modeling human belief would be helpful. If the AI doesn't actually intrinsically care about what we want, then it doesn't matter if it's modeling our belief, it just has other goals than us. And I think this could happen in a couple ways. It could happen, one, just that I think we could just end up with AIs that have their own internal goals. And I think another way is with multi-agent systems. I think we'll end up seeing I think we're headed toward a world where there will be lots of agents all interacting with each other. And I think we'll find emergent behaviors, just how like individual humans collectively start forming corporations. And then there's this question of how do you align the corporation? I could imagine AI systems, there'll be many of them interacting and forming lots of different subgroups. And how do we align this whole system of agents where I think, yeah, essentially that's not necessarily a question of modeling individual human belief, but a question of how do we actually control all this emergent behavior that's happening. So I think, yeah, how do we understand the emergent drives of individual AI agents? And how do we understand the drives of these collective groups of AIs are a couple problems that I think are quite important that modeling human belief alone isn't going to get us there.
Wow, that sounds like, yeah, a lot to hold in your head. But I guess you have to start somewhere. So, okay, awesome. Yeah, I'm also really curious. Those are a little bit more general questions, but if someone new was like coming to the field and was like trying to help you and your guys' work along, are there specific areas that you would guide them to? I guess the future work that you list here, you already mentioned some of this is actually what you were taking on, but is there something that you would like others to help with, like some kind of collaboration request, or at least like a pointer to, as someone new entering the field, this is where there's still some gold to dig up, or at least some useful, like a useful place to look for possible work.
Totally. I think there's both theoretical and empirical directions here. On the empirical side, I think this question of partially observable RLHF is pretty ripe for empirical work. So for example, when I'd submitted this work to some conferences, for example, and a lot of the reviewers were asking, why should we care about this partially observable setting? Can't the human, for example, with that NVIDIA example I showed here, reviewers were saying, can't the human just see that the AI is hiding the error messages? And I think right now the field is very much in this chatbot mode where the field is thinking, hey, the AI's actions, it's just this short chat where the human can see everything that's happening in the chat. And I don't think the field is yet appreciating these agents are going to be able to do so much that humans don't see. Like they're going to be able to browse the web and humans aren't going to be able to see all of it. Or the AI is going to be able to execute code on lots of remote machines and the human's not going to see all of that. So I think, yeah, a super concrete place that I would suggest people think about is to think about applications. Yeah, if we think about applications of AI where the human's not going to see everything, then I think any kind of experimental work there is something that I think that is a great place where it's both ahead of the field in the sense that I don't think there are a lot of people right now working on that problem, but I think it's also quite tractable. And I think in the next year or two, we're going to see a lot more of these applications of partial observability. So I would suggest to someone new, like think of some example of an AI application or an AI agent that would be taking actions that you don't observe and see what happens when you try to apply RLHF in that setting and see if there are any improvements we can make to the process.
Amazing. Thank you so much. Yeah, that was super future facing as well. Thank you so much for the presentation. I think it was definitely complex, somewhat very sophisticated, but then you also anchored it in like really great examples. So thank you so much. I really learned a lot today. I really appreciate you coming on. Thanks everyone for your great questions. And yeah, I wish you much success with the work and hope it wasn't the last time that we see you here. Thank you so much.
Wonderful. Yeah, great to be here. Really appreciated all the questions and discussion.
All right. See you at the next one, everyone. Have a good one. Bye, Scott.